Divs know everything. She said you can use whatever.
All right. Welcome back, everybody. I'm trying to set up two devices today because I want to probably use my laptop for reviewing one of the Verilog-A files that I've uploaded on Canvas. It's difficult to do with iPad. That's why, when we get there, if we get there today, hopefully, then I'll be using the other device. Okay, so without further ado, in the last class, we discussed the basics and the necessity of compact modeling, right? And hopefully I was able to illustrate the power of compact model to go across multiple layers of abstraction, right? In design, in, regular nanoelectronic design. So today we're going to be very specific to a single platform for compact modeling that will be Verilog-A. But before that, I wanted to start with a different example that is not Verilog-A, just to show you that there are other options out there. Verilog-A is not the only option, right? But although it's the preferred option nowadays. So this is one example of a SPICE-based model. You guys mentioned that you have used LT-SPICE or some other versions of SPICE in different parts of your career, but maybe not all of you have used HSPICE. Typically, the model that I'm showing you here was implemented in HSPICE. But there are other versions of SPICE which are also used to develop models, like, for example, WR SPICE, and all sorts of other versions. Now, what's the foundational concept for SPICE-based compact modeling? If you can, so remember, the circuit simulator, SPICE is typically a circuit simulator, and the circuit simulators deal with KCL and KVL, right? They try to solve circuits. No matter what you do, they will try to come up with, summation of current, summation of voltage, and balance it out according to KCL and KVL, as you can imagine. Now, if you could somehow represent your device's characteristics in form of an equivalent circuit, okay? For example, a diode. How many of you have seen in probably 335 equivalent circuit of a diode or equivalent circuit small signal model of a MOSFET, right? There was a time when we didn't have that much powerful modeling tool like Verilog-A, for example. Then the only option to represent a device with unique feature was to come up with an equivalent circuit model. The good thing about circuits is typically with resistors, capacitors, and inductors, you could represent mostly anything. With sources, voltage sources, dependent and independent, you could represent mostly any type of phenomena. And turns out, just to take a tangent, very recently, people have demonstrated that circuits can be used to even represent quantum phenomena. You know why? Because, for example, Schrodinger's equation could be expressed in form of KCL and KVL. So if that is the case, then the paper was about how to represent Schrodinger's equation, which is the foundational equation for many quantum mechanical effects, right? If you can express that equation, then you could probably mimic most quantum effects with circuits. So obviously, just a very big stretch. But for our case, we are not dealing with that complex, right? Something with some unique features, maybe a ferroelectric, maybe a, memristor. You can come up with equivalent circuits to represent those devices. And when you do, you can incorporate that circuit in SPICE, because SPICE is essentially a circuit simulator, right? And you represent the characteristics of that device in form of a current or voltage, some kind of property of the circuit, typically current and voltage, because the circuit simulators will solve for current and voltage. So oftentimes, what you're looking at here in this slide is a SPICE-based model for a ferroelectric transistor. Okay, a ferroelectric transistor has just a basic transistor with a ferroelectric connected to the gate. As simple as that. One extra layer of ferroelectric material. For whatever reason, there are multiple reasons why you might want to do that, but we don't care for this course. Now, it's a unique device with unique characteristics. How do you represent that? Sure, you can represent that using equivalent circuit. And I'm not getting into the detail of equivalent circuit. That's not the idea. I'm not trying to teach you that particular model. I'm showing you that this is a possibility that you can come up with. By the way, all of these that you see, these are oftentimes dependent voltage sources and bigger blocks. If you go deeper into this block, there will be smaller circuits. Okay, so essentially, the high-level picture is to represent a device with a equivalent circuit and then incorporate that in SPICE. And typically, SPICE does a very good job of solving that. Okay, what's the benefit of these models? They tend to be very easily implementable with other SPICE-based circuits because they are already in SPICE, seamless connectivity with rest of the circuits and systems. And oftentimes they tend to converge quickly because SPICE is a very efficient circuit solver. And when you're expressing this in circuits, by the way, there are other advantages. You don't have to worry about expressing the characteristics and properties in closed form equations. Maybe if the equations are so difficult, especially if it requires numerical solutions, then Verilog-A compact modeling can become tough, right? For that, circuit simulators are often, our places to be. Okay. Now, just wanted to show, once you have this model, so this is a model for, let me show you. This entire thing is a model for this ferroelectric transistor. And this is actually a symbol which shows that you have an extra capacitor. Fe stands for ferroelectric capacitor to the gate of the transistor. That's it. That's the device that you're dealing with. Okay. And then you can then use this model to simulate circuits like this. These are examples of where this model was used. So it's a SRAM circuit, as you can easily recognize, 6 transistors. Each one of these transistors would be a ferroelectric transistor, okay? And you can easily use those models to simulate that and get useful characteristics out of it. Okay, and this is literally a screenshot from the paper, as you see. Okay, so SPICE-based modeling is possible, but it is not ubiquitous. Not everybody has access to HSPICE. Not everybody will be using HSPICE for their simulations. For example, those of you who use Cadence mostly, typically the simulator that is coupled to Cadence is Spectre, right? Yeah, you can also use SPICE, but for the most part, people use Spectre. So, all right, if you make a SPICE-based model, you cannot easily integrate that to Spectre. So you need a platform that is, capable of being connected to multiple simulators and, ubiquitous in general. So that's where Verilog-A comes in. So there are some unique advantages that Verilog-A brings, and we will, from now on, we'll only discuss about Verilog-A, right? We'll not really pay too much attention to SPICE-based modeling and others. Okay, so Verilog-A is an HDL or hardware description language. There are other hardware description languages that you may have learned, right? Remember, don't mix it up with conventional Verilog. Okay, Verilog-A and Verilog are not the same. Okay, that's something that people often misunderstand. Typically, A stands for analog. There is a reason why we mention that, because for the most part, it is very powerful when it comes to mimicking analog properties, right? If it is just zeros and ones, then we have other, simulators and other modeling tools that we could use just for digital electronics, simpler to represent. But analog electronics, for example, a memristor is a fully analog device. It feels like it has 2 states, like low and high resistance state, but practically the resistance levels are nonlinear and they vary gradually. And there could be multiple levels of resistance as well. So for the most part, these emerging devices and materials are analog in their characteristics. So Verilog-A is very useful in modeling them. Okay, so Verilog-A can describe a wide range of conservative systems and signal flow systems like electrical, mechanical, fluid dynamics, and thermodynamic systems. You see the point here? So it is not only useful for electrical system, it can be used for anything almost. But for the most part, for the sake of this course, we're only interested in its electrical usage, obviously. Now, the most powerful thing is that the ability to add models to a circuit simulator, such as SPICE, dramatically increases the range and makes it immensely powerful. What it means is, obviously, if you are using LT-SPICE, one of the downside of using LT-SPICE when it comes to circuit simulation is that you are stuck with whatever components are available with LT-SPICE. Okay, imagine, have you ever tried using LT-SPICE for memristors, for example? Hey, I want to incorporate memristors in this circuit. Okay, you have to come up with a circuit equivalent of memristor first. You cannot just plug in a small, closed from compact model from external sources. Okay, now how about spintronic magnetic tunnel junction, for example? Okay, it's very difficult to represent that in circuit based representation. It's not impossible, but very difficult. So you are stuck for the most part. And oftentimes when we represent something in terms of equivalent circuits, remember, we ignore many effects. We ignore many effects to make the circuit feasible or, to help with the convergence issues. So for that, it is not the most ideal thing to try to always represent everything with circuits. But imagine if your simulator could just take in an external block, like external file, and read from the file and reproduce all the characteristics. That would be very powerful. So that's what Verilog-A does. So when you make a model for, say, a magnetic tunnel junction in Verilog-A, you can then import that file. You don't have to embed that within the simulator itself. You can import it as an independent file in HSpice code or in Spectre code, okay, wherever you want. So that's very powerful, and you will quickly realize it with some hands-on activities that you'll do as part of your project. Okay, Verilog-A language has analog operators. This is important for time derivative. So it has DDT, time integral. It also has integral features, which I don't recommend using for most circuits. It leads to some challenges. Linear time delay, Laplace transform, Z transform. So there are many built-in features that Verilog-A provides. It's almost like, MATLAB, I would say. Like many of the features that MATLAB provides, Verilog-A also provides. It also has if-else condition, which you can use. I mean, just imagine making a simple model for a device that we discussed. Remember in the last class, we talked about vanadium oxide that exhibits insulator metal transition. Now, if you're trying to make a model in Verilog-A and you don't want to do anything fancy, like super basic, you could just say, if the voltage is below so-and-so, show this resistance. If the voltage is above so-and-so, show the other. You could just do a if-else type model, which is typically not done for the simple reason of, I hope you remember that, there is a principle of compact modeling. If something dramatically switches from one level to the other, there is a sharp, increase in the derivative. Remember, make sure the derivatives are smooth. So when you do, if something happens, do this, else do something else. There is a sharp transition at a given threshold. Don't you think? At that threshold, what is the derivative? I mean, if it is I versus V, the derivative of di over dV will be infinity, as you can see, which is going to lead to convergence issues. All right. So you could do that if you wanted to, but we typically don't do it for most modeling approaches. We use if-else for something intermediary, but when it comes to I and V, we always use some smoothing factors or some other aspects to the model. So we are getting there. We'll see some examples. All right. So some basic components of Verilog-A. By the way, if you are wondering, will we have to develop a Verilog-A model of our own as part of this course? Given the time and the limitations of, number of weeks we have in hand, and also the amount of materials we have to cover for this course, I don't want to make you develop a model from scratch. What I will have you do is use an existing model to simulate, to get yourself familiarized with how to use it, the power of Verilog-A models, and then maybe while you're doing it, you can open a model and see how it is done. Okay, you don't have to make a model of huge complexity, but every once in a while in your career, you might want to create a model for something simple. Okay? So that is definitely on the table, using Verilog-A model, but not making the model from scratch. But typically that also helps, especially if you open up a model. How do you handle parameters? How do you change the model and update the model for your benefit? That is often handy. Oftentimes we get models for free from other groups, and then we update those models to add features or to repurpose it for some other devices that comes in the future. So if you can understand the syntax, if you can understand the approach towards modeling, it is easier for you to make those tweaks rather than make something from the scratch. Because you will see the model that I will show you, it can be fairly complicated if the model is well done. Okay, so like C coding and other coding, you start with some header files, which typically defines all the electrical disciplines. Like how does the simulator know how KCL and KVL will be handled within the model? So all of this definition is, basically hidden from the user. So all you have to do is always include these header files, and they will take care of most things. Include constants VAMs. It's basically, it includes a lot of constants that you might use. For example, m underscore pi, it represents the value of pi. M represents mathematical parameter. Okay. So for example, there are parameters for the charge of an electron. There are some other parameters like epsilon 0, which is like free space permeability. So all of these parameters, most of these that you might want to use, are typically included here. You are also able to define parameters like this within the code. Like, for example, if you want, you can define a parameter like this. This is defining pi, which is not recommended. It is always recommended to use the parameters from constant.vems, especially because the high precision that they provide. When you define pi as 3.14, you're losing a lot of precision, which can add up in large scale circuit simulations. Okay, here is how you comment, because that's the first thing we always need in any coding. Just double slash. And if you want to comment multiple lines, here is how you do it. Okay, we'll see a realistic file soon, don't worry. But before we go there, it is easier to digest these small snippets than to look at the entire code simultaneously. Okay, so the next thing, you always start and end with module. So you start with module and you have to end the module, and everything that you do will have to be within these 2 bounds, module and my end module. And you have to give it a name, my module or whatever module. Imagine you're trying to make a model for memristor, you can say my memristor. And by the way, my is not a necessity. I'm just saying memristor 1 or whatever, right? But remember, this is something that often is misunderstood or mistaken. When you save the file as .va extension, you give it the exact same name as the module name. You see what I mean? So if your module name is memristor, file has to be saved as memristor.va. Okay. Otherwise, you might get an error. All right. So, all right, then you have to define within the modules, by the way, everything is within the module and module description. You have to define the inputs and outputs, okay? Because the way we view a model is a black box, and it has a few sets of inputs and sets of outputs, and you have to define those inputs and outputs. Why? First of all, when it solves KCL and KVL and tries to look for branch currents, it will get all the inputs and all the outputs and treat them as electrical branches, okay? And there is a reason why I'm mentioning that here, because of the second line. It's coming. First, you define your input and output ports. So these are in-out, meaning this could be used as input or output, doesn't matter. Okay? And next, you are defining these ports as electrical. Notice, all of the ports that were in-out are also mentioned as electric. By the way, in what kind of situation you can deal with in-out ports? Imagine you have a resistor, N1 and N2, 2 nodes. You can use either of them to provide a current, don't you think? So this node could be used as an input or as an output, by the way. You can take an output from that node as well. Okay, for electrical, imagine I add some extra port 3, port 4, but they don't really exist. They're just virtual port. Oftentimes, for the sake of modeling, we create virtual ports within the model, which are not supposed to be participating in KCL and KVL formation because they don't exist. They're just helping me do some intermediate calculations. Okay? So if you don't specifically mention that these are not electrical ports, then SPICE will try to solve KCL, KVL in those ports as well. Does that make sense, folks? Okay, let me show you one thing as to what I mean by that. Notice, in this is not in Verilog-A, but in Verilog-A, similar situations could arise. This is in SPICE. So notice, this is an independent block. It is not going anywhere. Is it going anywhere? No, it's basically an independent circuit. Okay, so what it does is it calculates something, and that something, say QP, is then used in a different portion of the circuit. So they're not physically connected. So this is an intermediate stage. It is helping me calculate something, and that is being used somewhere else. Okay? So when you try to solve KCL and KVL, there is no connection between these 2 circuits. How do you solve KCL? Right? So you get error from circuit simulators, unless you mention which of these ports are not electrical ports. They're supposed to be intermediate ports. Okay? So for this example, both our ports are defined as electrical. But when you have extra ports, you don't define the others, virtual ports, as electrical. So SPICE only treats these ports to solve KCL and KVL. Does that make sense? Okay. All right. And then obviously, in any kind of modeling, you have to have parameters. How do you define parameter? This is how you do it. Parameter real, because these are real number, and you give it a name, you give it a value, you give it a range. Typically, that's advisable to always use a range for parameters if you know the range. If nothing, you can still tell 0 to infinity. or negative infinity to minus infinity, but still provide a range. Okay, we'll get there why that is the case. The second example shows you that parameters could also be compound parameters, meaning, so you've defined one parameter here, another one next to it, and the third one here. And when it comes to compound parameters, you can use the previous parameters to calculate something in line, which is also possible. Remember, whatever parameter you define this way can be passed from the circuit simulator without getting inside the model. Even if you don't, sometimes when people share models, they basically encrypt the model. You cannot open it and see how the model is done. All you know is a set of parameters that you can pass. Okay, parameter A, B, C, D, you can pass from the code in the circuit simulator level. Okay, remember, you can only pass the parameters that are defined within the block, like this. Are you all on the same page? Okay, so if you don't have a parameter called X, you cannot pass this parameter to the model. Even if you realize, oh, I want, for example, you can use something without defining it as a parameter. You can use something. You can assign X equal 1 and then keep using X throughout your code. That's fine. But remember, you cannot use that X as a parameter that you can change later from your circuit level code. That is hard-coded. But these parameters can be manipulated from external circuitry. So for example, this is your, I'm fast forwarding just to show you how things look like. This is your Verilog-A code. It will be hidden somewhere in a file, .va file. You may or may not ever open it. All you know is how to call this file in your simulator. So here is how you call this file. Notice, this is what I mean. I'm just fast forwarding to make a point here. Okay, .hdl, and you give the name of the file, simple resistance or simple res.va. So you're calling the file, you're including the file here, all right? And then you instantiate the device you want to model. So this is a Verilog-A model for a simple resistor. Okay, we are getting there. We haven't covered everything, so I'm not explaining the code yet. But at least see that this is a module in module. So it is a module for a simple resistance. Here is how you instantiate the resistance in a circuit simulator. This is in HSpice. This is in Spectre. You see they have different syntax, but doesn't matter. You know the syntax, you can use them. So you start with always X, and then you give it a name. You can mention X resistance, X1, XA, whatever, but it always starts with an X if it is a Verilog-A model. Okay, all right. So for this example, this is X1, and then where will this resistor be connected? You need two nodes, right? And the nodes are, so imagine you are trying to model something like this. You have a voltage source, you have a resistance. This is top, this is ground, 0. That's how it is named. Okay, super simple. So you provide the node names, top and ground. Ground is typically always mentioned as 0. Okay, and then you add the name of the module. Remember, simple res. Did you see that here? The module name was also simple res, and the file name as it was saved was also the same. That is necessary. Okay, it's not by chance. Okay, so you call the name of the device that you are modeling, and then what? Notice, this is what I'm talking about. And then you send R equals 2 kilo, like 2 kilo ohm resistance, all right? Because the reason I can do it is, notice, R was defined as a parameter. And when you define it as a parameter, you have to give it a value, just as to initialize the value. And the value was like 1K. But that doesn't matter. The model will only use the value that you pass from this line. Are you still with me? So this is what you can do if you define it as a parameter. Now, if I don't use this line at all, I just stop at simple res, then what? Then it will use the default value that you set inside. Are we all on the same page? Okay. Now, what I'm saying is, imagine for internal calculation, you had another parameter that you define, say X equals 10, something, and you used X somehow, okay, something, V times X, something like that. I'm just making everything up here. Some internal parameter that you used so for some calculation. Can I change X from here? Instead of 10, can I do it 15? I cannot, because I haven't defined X as an explicit parameter here. That's what I'm saying. Okay. All right. So getting back to the point here, we typically try to define all the parameters in line before we begin coding, so that you at least have the option to change them at will. Otherwise, you will never be able to do that. Oh, next, move on. Okay. After you make the module, remember, this is the structure. Everything happens within module and end module. That's the final bound. And module and within module and end module, you first define the input output ports like this. Excuse me. And then you define the parameters. This is the hierarchy. Start with defining all the ports, and then define all the parameters you need to model. And then you actually go and do the action, do the electrical action that should occur. And that happens within the analog module. Analog, begin and end. And this is super simple, just one sentence here, but it could be really complex, really large. And I will show you one realistic example today. So within analog begin and end, you define how the device should behave. So for this particular case, are you still with me? Okay. Just to highlight a couple of things here. There are many new information in this slide, so we need to pay attention to this. First of all, notice what it is trying to do. It is trying to do Ohm's law. It's a resistor. It should obey Ohm's law, V equals IR, or in other words, I equals V over R, right? So we're trying to see the current that should flow through this device. And the node names have been set as A and B, for example. A and B are the node names. And the current, here is how you represent a branch current. Imagine you have a branch between node A and B. The way you represent a branch current is I, A, comma, B. Simple? Okay. The way you define the voltage difference between two nodes is V, A, comma, B. Or you could also do VA minus VB. This is also possible, individual node voltages. But typically, to make the coding cleaner, we use this type of representation. Okay, so super simple. Voltage between A and B divided by the parameter resistance will be the current through the branch. As simple as that. That's how you make a resistance. Okay. Now, let's make it a little bit complex, a little bit more complex. Did you notice that we didn't use equal here? We are using a different parameter, different operator called the contribution operator. It means this component of current will contribute towards the branch current, but there might be other sources. And in the next example, you see the second source, which incorporates noise. So thermal noise. It's not just the voltage that you supply that generates current. Because of thermal noise, there will always be a thermal voltage automatically generated, and that could lead to some degree of extra fluctuating current. And that's how you represent it. So this is a contribution operator, means this will contribute to the branch current IAB. The next one will also contribute to the branch current IAB, and so on. Are you still with me? Okay. By the way, what it is doing is thermal noise is represented as 4 kBT. Boltzmann constant is K, T is the temperature, and so on. Like I said, there are many new things here. First of all, 4 is 4, and then you are multiplying it with kBT. Notice, how do we represent Boltzmann constant? It's a parameter underscore K, and this tilde is part of how you use those predefined parameters. It is included in the constants.vems. Does that make sense? There is a list. You don't have to memorize this. You can just look up from the list what parameters are available. It's more than you ever need, but you can use it automatically. Now, this is how you call temperature. See that? You can request for the simulation temperature. And where does it come from? When you simulate in SPICE, most simulator will allow you to set the temperature for simulation. Okay? Does that make sense? You can simulate .temp something. You can always set the temperature for simulation. Whether or not that translate into something, that depends on the other models. There are some transistor model which handles temperature. There are some that don't. They're just calibrated for one temperature. So even if you change the temperature, nothing changes internally. it gives you the same result. So a simulator, it's actually dangerous sometimes to work with simulators. Why? Because it will give you something, no matter what you do. But you have to really check whether these numbers are believable or not. You have to make sure everything is, set accordingly. So you cannot just rest assured that I used .temp and I changed the temperature to 300 Kelvin. That doesn't mean there was actually something happening inside the model if the model doesn't handle the temperature. Okay. Anyways, so why am I telling you this? So this additional line is bringing temperature to the mix, and based on the temperature that you're setting, notice this white noise is a function. You are not defining this function. It is available in Verilog-A. Verilog-A allows you to generate white noise. Does that make sense? Isn't that powerful? So it is generating white noise based on the equation that we know of white noise, and it is a thermal property. So it is allowing you to incorporate this thermal fluctuation within the device that was otherwise very simple to work with. So now that you've incorporated this contribution as well, when you simulate in spice and set a temperature, that will have an effect. Otherwise, if you just go with this model, who cares? If you change temperature, nothing changes. Are you all okay so far? Okay. And notice the contribution operator ensures that all of these components, there is just two here, but there could be many components, they cater to the needs of branch currents. Yes.
I accidentally set this to an equal sign. So like going down the string, I would have this last line would just be white.
Exactly.
The contribution.
Yes. Well, it will be wiped out. So if you accidentally use equal sign, that's it. It is the number, nothing else. Okay. So typically, even if there is just one branch, notice, even if there is just one branch, it is advisable to never use, equal sign. Because what if you try to add an extra feature, extra effect later on? Then you forget to change the equal sign somewhere. It disrupts the overall flow. Okay. At that situation, oh, by the way, let me just complete this and I'll show you a different example as a tangent, but meaningful tangent. Notice you can also define strings in Verilog-A. It's rarely used. I never used it in my coding typically, but you can. Like in C coding, for example, you can define strings. Here is exactly the same. You can define string. And then important thing is what I just mentioned in the previous slide. When you define parameter, you can also mention a range. Let me just zoom in here. So notice this is an integer. This is the name of the parameter. This is the value that you assign. And then this is the range. And I hope you guys understand what this and that means. Close bracket, open bracket, right? Less or equal, greater. So basically it means this pos value will be greater than 0, but less or equal 40. Okay. Are you all good? All right. There is a reason why you might want to do that. And I'll show you one example why setting these bounds, ranges, is absolutely critical to ensure convergence and to ensure quick convergence. By the way, if you don't provide a range, models could take up any random value at any sort, or sometimes because of mistakes, you can pass values that is, okay, imagine you calibrated your device with experiment for a certain range of parameters. You don't want your users to ever go beyond that parameter because the model will give it something. And then you will blame the modeler that, hey, your model is giving me wrong results. Then you have to go debug and say, hey, you didn't pass the right parameters. You're not supposed to use these parameters at all. Okay? Because you'll be surprised to see what kind of numbers people can use with your models, especially when you share the model openly. So they get garbage results and they blame it on you, that your model is useless. And then you have to justify somehow. It's never fun. So to avoid those kind of scenarios, you have to always set the range that you want to be set. Now, if somebody tries to pass a parameter from externally, like obviously from spice level, that is outside the range, he or she will get an error. So that's how you know you're not supposed to use that parameter. Okay. By the way, you can also use this type of sub-parameter definition. Notice, parameter defining as low and high, and then you use those parameters to set the range. Okay, typically, it's the cleaner approach. Why? Imagine you are using the same range for many parameters down the line. And I will show you, like I said, a realistic code. You can have 50, 60, 70 different parameters. Okay, it's not just 2 that you can manually change. Now, for some reason, you want to change this 40 to 30. and it is used in like 100 parameters. You have to go and manually change all of them, which is a pain. And more importantly, you can miss one, and then that will lead to error. So it's better to always have a high-level parameter if you are reusing something, and then change that. If you change low to 10, from 10 to 15, fine. Everything else changes following it. It's good practice. Okay. If you're wondering, this is an interesting sentence that I want to highlight here. Yeah, you define a parameter as an integer, you give it a default value, and then here comes the range. You can define it from 0 to infinity. Okay. Notice infinity is always open-ended because you can never equal infinity, by the way. It is always open-ended. But you exclude a range. You see my point here? So from 0 to infinity, it has everything. But there is a range that cannot be used, and you exclude that range. So this is an extra feature. At some point, I was looking for a feature like this. I didn't know. I looked it up and I found it. Oh, wow, it already exists. Otherwise, it's difficult, right? How do you... And by the way, there is another value that you don't like. You can also exclude specific number. Never use 5 for whatever reason. Okay? Are you all good so far? Okay. So this can be handy, by the way, if you're making a model and you realize that your model is fine, but there is... Remember, all of these models are mathematical tools, and mathematics can be weird. For one specific value, it breaks down. Everything else it's fine. Okay? There is a numerical situation that this value cannot be ever used, and it cannot physically be used, for example, for some reason. How do you exclude that value? When you simulate, the simulator, by the way, you no longer have control. The simulator takes up random value, Newton-Raphson method. It takes a random set of solution to the node voltages, try to converge to the eventual solution. And in doing so, it could end up with any value in between, right? So if you don't exclude certain conditions where you have non-convergence for sure, then nothing works. You don't have a working model. But maybe you run the model, but you exclude that specific number of that parameter that you're dealing with. That is a possibility, okay? That's how your model at least works, but for that specific parameter, you just skip it. Okay, now I will take a step back and remember this contribution parameter here. There are like two sections, two contributing factors. Let me go back and show you something here. In this model, this was a model for a 2D memristor, 2D material memristor using molybdenum telluride. Okay, turns out the current, when current flows through the molybdenum telluride layer, there are three components that take effect, that lead to the total current simultaneously. They always take part. Okay, one is the direct tunneling. If I just try to explain it briefly. So there was a situation like this. When tunneling occurs through this regular band, it is called direct tunneling. It's a rectangular barrier. When tunneling occurs through this triangular barrier, it is Fowler-Nordheim tunneling. Okay, FNT. Different type of tunneling. Tunneling, but the equations are very different. You see, this is Fowler-Nordheim tunneling. This is direct tunneling. The expressions themselves are very different, as you can see. They depend on different things. They can be influenced by different parameters, not the same, obviously. So you have to account for them separately. So Fowler-Nordheim tunneling, direct tunneling. And there was one more thing. It's called thermionic injection, or taking heat and not tunneling, just getting to the other side because of thermionic injection. Okay? So that's also known as the Schottky component, Schottky barrier injection. So these three components take place simultaneously. So these are current density, but you can just use it as current, Schottky current, Fowler-Nordheim tunneling current, direct tunneling current. So you have three current components contributing to the same branch. I hope you can see the picture here. We'll be using contribution operator for this, contribution operator for second one, contribution operator for the third one, to make sure all of these three components are handled simultaneously. If I assign equal, then it will be just direct tunneling, just Fowler-Nordheim tunneling. Because turns out, this is not showing you that trend. In certain range of voltage, one component takes over the other. Are you all good so far? So when you consider them simultaneously, in lower voltages, direct Schottky is like almost non-existent, very low. When you go for higher voltages, some other component becomes prominent. So all these effects can be seen when you use the contribution operator to include them always. Okay, anyways, so let's move to the next one. Next slide. We have already kind of touched upon this slide, but let me just revise it again. Notice this is a full-fledged Verilog-A code. Super simple, obviously, but at least gives you the, the sections, all the useful sections. You start by including the disciplines VM always, and then I recommend including the constants.vams as well. Although there are no constants used here, but what if you want to use it? And then within the module and end module, everything happens. You first define the set of inputs and define the ones that are electrical input output. And then you define the parameters. And within the analog begin and end section, you define the effect, define what it should. So the example that I just gave you for the memristor, the equation will not be as simple as V over R, will it? It will be what you saw in the equations. You could just plug in those equations, literally. That's why it is so powerful. Because we understand the expression, understand how it changes. Just take this and copy paste it here. Imagine how many parameters you'll have to define. You see that? Easily. And here, how many parameters? How many parameters? Many parameters, of course. And then you have to be mindful of the ranges of every parameter. Some of these parameters will be available in constant.vams, like KBT, for example, where it is. Boltzmann constant, pi. See? So you need all of this. What I'm telling you, these are definitely used in actual modeling. But the power is you can use this equation, copy paste it there, and then make sure all the parameters are accounted for accordingly. So that's what makes it very powerful. A model can now handle all of these equations. But notice, all of these are uniqueness of this approach is these are closed form equation, that your current is equal to something, current equal to something, current equals something. That's why you can do this super easy modeling. But obviously, you have to first derive them to be able to model them. But once you derive them, modeling is easy. But if you cannot simply derive them, there are devices where it is impossible to derive. Then Verilog-A modeling is tricky. That's why we have other models, as I told you, right? Lookup table or machine learning based models and whatnot. Okay. Moving to the next. Oh, by the way, this is how you define it in HSpice. This is how you define it in Spectre. Different syntax, but it's pretty much the same. Okay. Some resources, you have access to the slide. If you want to learn more, just click on any of these links and you'll find more details about them. NEEDS stands for Nano Engineered Electronic Devices and Systems. It's a portal basically supported by Purdue. NanoHub is also supported by Purdue specifically. It's a very good resource. They share free compact models with you. And in fact, I'll have you make use of one of those free models, so that first of all, you familiarize yourself with this portal that exists. Okay, something free. And those models are made by many universities, including MIT, Stanford, Berkeley. There are many models from Purdue and many other places, not only in the US, around the world. Okay, so they make models and they upload the models. And by the way, these are reviewed. You cannot just upload anything. That, hey, I made a model, upload it. No, it's not like uploading a photo on Facebook. Okay, I don't care. I can do anything. Here, there will be reviews, obviously. They will make sure that your model is up to certain standard. It meets the requirement. There are certain documentation requirement, and then they will let you upload the model. What's in it for you? Well, prestige, that people are using your model and they will cite your work. Okay, if I write papers, I remember I cited a model for more than, 40, 50 times already. One particular model from a group, from a research group. So just imagine that group got 50 citations from me only. Right? So now imagine I'm just one person. There are so many other people using that model. So that can easily build up. It's kind of sharing codes in online repositories that people can reuse, open access. But not everybody feels comfortable sharing their code for multiple reasons. Sometimes there is a malpractice that people take somebody's code, make some modifications, and try to publish a paper as a new model. It happened before. So that's why people often use encryption to share their model. I'm giving you my model, you can use it, but you cannot change it. You cannot change it because you don't have access to the internal code of the model. That is also a possibility. Okay. All right. The second reason why they want to do it is because what I just explained. People take the model and use any random parameter to run simulations. And they get random numbers. And when their papers are retracted, they blame the modeler that, hey, your model gave us unreasonable numbers. But it's not the fault of the model. It's the fault of the user. Okay. Anyways, and there are many models that are available and used by industry as well, by the way. It's not just academia who use these models. BSIM model is heavily used in industry. I personally used them when I was in a Global Foundry as an intern, I remember. And these models are typically made and handled by Berkeley folks. There is a group at Berkeley who are like super famous for this. There are other groups. When I was a graduate student, they were at Arizona State University, and now they moved to Minnesota. They make predictive technology models, PTM. These are kind of very useful model for academics because they're open source. They reasonably mimic the characteristics of advanced transistors, but you have up to 7 nanometer. They haven't made anything under that. And all the other models that are typically still under wraps, and they will publish it once they're done using it. Typically, that's the other trend. Very few groups will publish their model that is the most cutting edge one. They will use the model for years, write papers, publish papers, and once they're done, okay, we have had enough of this model. Let's move on to something else. Let's share this model for other people to work on, and they share it openly. All right. Anyway, so that's why we don't have the compact model available for most advanced transistors yet. If you want that, you have to make it on your own. So anyways, coding guidelines. I already expressed a few things, obviously. I don't have to tell you that indenting is very important. Typically use a space, not tab. I'll show you some example. Always comment your code and use meaningful variable names. Don't just use x1, x2, x7, x17. Give it meaningful names so that you can recognize what this parameter is doing. And before I go there, I will explain what aligning equations vertically on this mean. Let me just fast forward here. You see that? Notice when you're defining parameters, you're trying to align the equal signs together so that it is readable. When you are aligning the other code, try to align it with respect to the contribution operator so that it is readable. Okay, that's the suggestion. Okay, now the final comment: do not lump everything in one equation like this. What does that mean? So this is another expression for a resistance. Resistance could be tricky, by the way. I remember I attended a workshop, a compact modeling workshop. When I first started as a PhD student, like very first time, within a month or so, I was sent to participate in a workshop, like a 2-day-long workshop on compact modeling, specifically compact modeling, just to learn how to do compact modeling. And throughout that workshop, 2-day workshop, they made us work on making a model for a resistor. I mean, would you believe it? Resistor. I used the same resource. I shared it with you. The model that was made as part of the workshop. You'll see that just to make the model for a resistor, you could have so many different considerations that, and this is done in industry because industry has to sell product that works, right? In academia, I could just go with this V equals I over R, done. Write papers, get away with it. But in industry, it has to be so sophisticated. And you'll see it in a few minutes. Okay, so, but long story short, in a simple resistance, there could be so many different factors putting in there. This tiny factor that you see here, this one, this is incorporating self-heating, meaning as current flows through the resistor, it generates Joule heating and it heats itself up. It changes its own resistance and blah, blah. There is a positive feedback going on there. So this self-heating effect is incorporated using this expression. I mean, you don't know it unless somebody uses comment and mentions what. But notice that something that's strong about this expression is that, first of all, it has used equal sign and has treated all these components additively. Like basically, this is the Joule heating factor. They have added everything, lumped everything together. Rather than doing so, it is always advisable to use individual contribution using contribution operators. Does that make sense? Okay. There are reasons, of course. First of all, readability. Second, it could lead to some errors because in some cases, not everything is additive. Sometimes it could be subtracted out of it as well. But anyways, we're getting there when you see the code. But point is, don't lump everything together. Separate them out into contribution operators. That is the idea. Okay. This is a screenshot from the code that I'm going to show you, a specific screenshot. Always use comments like this and use references to docs. You have to create a separate, that's the requirement for needs NanoHub model upload. you have to create a separate document, like writing a paper. And you have to refer to, for example, equation 5.17 is being incorporated here, so that they can go back and see what you're actually doing, rather than just relying on some bunch of codes. Okay. All right. So there is something wrong about this. That is being showed. Mixing tabs and spaces. That's why it looks messy, but don't mix them, obviously. One other example that is shown here is an error. This is a fact. This is a parameter 5b. You have set the value 1.2, but the problem is you haven't set any range. Okay, any range. Here. By the way, this is what I'm doing. Like I said, I told you I made these slides myself. I'm using all resources from the workshop. Of course, I cannot give you 2 days worth of material. I'm sharing whatever is easy enough to share for you to be a user, rather than a developer of Verilog-A code, because that is significantly more challenging, of course. But you can still try to edit somebody else's codes. At least you get a code, you need to do something. People can make mistakes, and you are running into issues in your simulation. You can fix them. So this is one example. This was a homework. Like, there were so many homeworks during the workshop. Like every time they teach something and they give it a homework, you have to do it right there. It was fun. It was very intense, but obviously very useful as well. So how do you debug? So this is part of a debugging exercise. Okay, the debugging was, why is it not converging? Where are you getting the problem? So when you get the error message, you have to debug the error message, and apparently the problem is coming from here. Notice there is a square root. By the way, that's the other thing. Verilog-A gives you these functions, log, like ln, basically. It gives you functions like square root, which you can easily use, like MATLAB, for example. So this is a square root function. Within square root, you have 5b. I don't have to tell you, if you have square root of -2, it's going to be a problem in your simulation, don't you think? It will give you imaginary number. So, of course, you got it. How can you make sure that you don't get a math error here? How do you ensure that? Set a range in 5b. You thought that your 5b is always good, is positive. I've set a positive value. Sure. But somebody tried to vary 5b in the code, and they started from -5 to 5. And then getting math error. I don't know why, because oftentimes if you have seen errors, they don't give you the specific. They just tell you math error, non-convergence, something like that. It becomes really tricky to debug at that time. Okay. So anyways, debugging is never fun. So better set a range from 0 to some other value, so that it can never be set to negative. Okay. And if you set a range and then try to vary, it will tell you exactly what is going on, what is wrong. And that is easier to debug and solve. Okay. Oh, by the way, another suggestion here. In this code, notice I told you that you can also have, 2 nodes, B and SI. For some reason, this was used. Of course, this is taken from a real model. That's why there is a meaning for SI here. So you could also, when you try to take the voltage difference between these 2 nodes, you can do VB minus VSI. It's definitely possible, but it is advisable to use branch voltages like V, BSI, particularly for readability. Okay? For readability. Anyways, okay. Obviously, as I don't have to tell you more. If you are not consistent with indentation, that's not good. Better is always stay consistent. There's nothing to see here. Okay. Common mistakes. Notice. First of all, always use SI units. Typically, Verilog-A model assumes SI units. Sometimes we forget that some variables are not in SI units. So you have to convert. Sometimes, for example, 5b, as I showed you, the value that you saw here, this is basically a barrier height. 5b is a Schottky barrier height. Okay. It's 1.2. It is typically represented in electron volt. So it's not SI unit. Okay, remember that. But everything else is SI unit. But here it is not. So you take the number from textbook or literature. Oh, what is 5b 1.2? Put it there. Remember, it's not SI unit, it's electron volt. So you have to convert it to joule. Or wherever you are using it, you have to be mindful that this is not SI. So you have to account for it accordingly in the equation. Which one is easy to make sure everything is SI, for example, right? So keep in mind, everything else is SI unit, whether you need it or not. do not mix case of parameters, meaning there are some simulators like HSpice that is case insensitive. If you write XS versus XS versus XS, like doesn't matter. It treats it exactly the same. Lowercase n1 or uppercase n1 doesn't matter, exactly the same. It will treat it as the same node. But not every simulator is like that. Some are case sensitive. So it's better in your Verilog. Verilog-A itself is case sensitive. It is case sensitive, okay? But not every simulator is. So be mindful of, don't use a parameter with uppercase and lowercase, assuming that all the simulators will handle it. You see my point here? Maybe you use transistor and lowercase transistor. You assume that they are two different parameters. They may not be treated the same in the simulator. So always mix and match, meaning transistor 1, transistor 2. That makes it completely different. Don't rely on the case sensitivity. But Verilog-A itself is case sensitive. Remember that. Okay, so typically Verilog uses ln, okay, e-based log instead of log, 10-based log, all right? Just keep it. You can always convert any of the log to the other, as you know, with a factor, right? 2.303. You can just change ln to log or log to ln, doesn't matter. Okay. Use, well, basically this is an example. I mean, people, when they code in Python for a while, they forget to do so. That's why. So imagine this is an if-else condition. If something happens, do something like that. But remember, everything has to be within begin and end. So that's something that I wanted to point out. All right. Another thing to keep in mind is tolerance and convergence issues. SPICE, when you remember, you are making this model to be eventually used in SPICE or other circuit simulators. And circuit simulators have different levels of tolerances. Okay. The way they work is they try to make summation of current 0. That's how, like, this is what KCL is. Summation of all the currents across all the branches is always 0. You know that, right? Super simple, KCL. So you have to get 0. Until you get 0, your simulator will not converge. Okay. Now notice, because of precision, see this line here. If you just manually calculate, you have 1 ampere, negative 1 ampere, they will be cancelled out. 1 picoamps, negative 1 picoamps, they will be cancelled out. Okay. But in your model, you are calculating step by step. You do one step, and then second step, then third step. You have multiple current contributions. One contribution, and I gave you the example which is completely relevant to this. I personally encountered it. So for low voltage levels, thermionic injection or Schottky current was super low, like picoamps, and the others are like microamps. So compared to one, the other becomes negligible if it is not properly handled. Okay, so notice when you calculate this to 1 ampere minus 1 picoampere, do you think 1 picoampere will have any effect? It will be ignored. It will be completely ignored. And you get 1 ampere because that's below precision. You get 1 ampere. And then you subtract out this 1 ampere from this one. So this is gone. But then you are left with 1 picoampere, which is not 0, by the way. So your simulator is trying to, come to a solution, but it will never get a solution. It is always getting non-zero. So your precision mismatch between Verilog-A steps and your SPICE simulator can lead to non-convergence. You see, we are so careful about convergence because if you make a model that doesn't converge, what is the use? Right? So that's why people have to pay a lot of attention into things like that. I told you, I'm not trying to make you make the models because that is very painful. That can be very painful if you're doing it right and including all the possible considerations. But using is not that difficult. You can always use it and modify if you want. Okay, so there is something called absolute tolerance, meaning you're telling the tolerance is 1 picoampere. Or you can always mention it as a percentage, 1% tolerance of whatever the value is. Both are possible to set. Okay, by the way, this is a solution, possible solution to this. If the flow of variables, like for example, current or charge are too small, we can get false convergence, meaning even when it is not supposed to converge to 0, because of ignoring that value entirely, you can lead to a convergence situation that completely ignores something. Okay, so how do you avoid that? The question is, okay, how do you deal with this 1 picoampere, 1 ampere, if it is below tolerance? Or some parameters, and I'm telling you stories from my life, personally, that I dealt with myself. So for example, in this situation, when you calculate, obviously I didn't just take this equation and spit it out. We had to calculate individually this part, this part, this part, and then put them on top of each other like many lines of codes, right? Who will just do, one huge line of coding? You cannot visualize this. It's like, you're typing, where was I? Did I cover this? Did I cover that? It becomes extremely messy. So you don't do that. What you do is you break it down into smaller chunks. Maybe this is A, this is B. So what you have is A minus B, right? You see my point here? So you make them into smaller sections, C, D, and then blah, 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 blah. So when you calculate A, maybe I arrive with a number that is super tiny. And then B, you get the point, right? So maybe A is 1 and B is 1 pico. And when you do 1 minus 1 pico is like ignored. That is like you're completely ignoring this part of the equation, right? Which is not right, for example. So what I'm telling you is when you individually calculate it, it is possible that, okay, it becomes particularly detrimental when, please bear with me. So this is A. Notice this. This is A, this is B. Okay. When you're calculating equations, you calculate A and calculate B. Somehow, in the next step, you calculate A minus B. Don't you think? You see that? You calculate A minus B. Okay. Imagine A minus B came down to 1 pico, like super simple, which is less than the tolerance limit that you set. And then it is actually assumed to be 0. It basically assumed to be 0. So what happens then? This entire numerator becomes 0. The calculator doesn't know that you are trying to do a bigger thing. It just calculates it every stage of the way. At any stage, if it is too small, it is treated as 0. And then this is completely gone. Like literally, you don't see any effect. I personally dealt with it, by the way. Hey, I should see more direct tunneling at this level of voltage, but it is not showing up. It's never showing up. Okay, let's comment out everything else and only see the direct tunneling. Then your current is 0. Basically, that means, so that's how you debug. So your current is 0. Oh, why is it 0? I've incorporated everything. Okay, that's what's going on. So that, now it's like super boring slide that shows you, okay, 1 ampere minus 1 pico is like, it can be a problem. But if you have it in mind, then you know, oh, okay, precision could be an issue. Let's calculate individually using MATLAB or something and see how the numbers look like. And when you see something that has lower precision, you can scale it up temporarily. Meaning you can use a factor. You can multiply it with 10 raised to 12 and make it artificially big so that it is not ignored. And what do you do next? Okay, so going back, sorry, I'm going back and forth, but I hope you're still with me, okay? So remember, A minus B came out to be a pico, but I deliberately will multiply when I calculate it in line with 10 raised to 12 to make it 1 so that it's not ignored, okay? And then when I put it back in here, notice here, and others, I'm eventually going to put all of these components in one lump equation, right? Here, I'll put 1 pico times 10 raised to 12 that I artificially introduced, and then I will again multiply it with 10 raised to minus 12 to get rid of the factor, scaling factor. Now that everything is in the mix, they will be treated together. They will not be ignored individually. So that is a technique that people often use and have to use, obviously, in many modeling approaches. Okay. All right. Let's fast forward to this one. Where is it? Okay, so rescaling is required. Scale up and then scale down. All right, testing the model, obviously, I will show you. You don't have to read it. I'll show you how to test the model, how to work on the model, basically using HSpice. We'll use HSpice, not Spectre, mostly HSpice. Okay, by the way, it's always a good idea after you make a model, always test it outside the measurement range and see what it does. If it is completely out of the way, you have to either specifically mention that don't use it, or if you could make it work or predict outside the range, that is always better because people want to use models that can predict beyond the experiments. If you're just only stuck with the experiment, that is not really that useful. It can be useful, but not that useful. Okay, consider unexpected parameter values. Why? Because if you don't get convergence issues, your users might get convergence issues. That's the challenge. All right. And all right, always when you make models, you always have to make models for N and P type. This is specifically for CMOS. And you have to run DC simulation, AC simulation, and transient analysis, because maybe a model doesn't have problem with one kind of simulation, but it has problem with the other. Okay, I particularly remember, there was a model that we made for ferroelectrics that where we ran into an issue that DC simulation didn't work, only transient worked. You know why? Can anybody guess why in a model only transient works but DC may not work? Can anybody guess? Just look at this slide. And DC, you know what DC is? There is no concept of time, as if you have given it infinite time, steady state. Okay, why is that? Why would it not give you the right result? Only transient gives you the right matching with experimental observation, and the others don't. Notice there is a derivative, time derivative here. So you're dealing with time. There is a how do you get a derivative? Okay, can you get a derivative from just one point? I give you one dot. Can you get a derivative? No, you need two. When you have two, you have a history. Previous point, current point. So previous current means there is a history. You have to have a history. Without that, you cannot compute derivative. Okay, when you do transient, you're going through time, you have history always. So you can keep calculating derivative. But when you go to DC, you cannot. So you had to come up with a way around to this problem. But long story short, you have to test it. And only then you realize, oh, there is a problem with my model. Okay, DC cannot be done. How can you do this? Eventually, we came up with an approach called quasi-DC, meaning you do first transient, and then what I mean by that is DC is essentially very low frequency transient. Okay, instead of 1 gigahertz, you do it in like 1 hertz. Okay, and then gradually ignore the time domain information. Anyways, so moving forward, that's the last slide. I'm trying to finish it up. So don't worry, this is the last slide. When you try to release a model, and I'm going to show you this, you don't have to just take this slide, but this is useful. You don't just release the source code. That's not how it works. You have to document everything, because without that, it is completely useless. Nobody can use your model. You have to provide sample parameter set and netlist. That, okay, for these parameters, this netlist, here is how it runs. If you ever want to upload your own model, okay? This is publishable, by the way. And like I said, it gets a lot of citation. And always use license term, meaning if you don't want somebody to use it for commercial purposes, maybe a startup takes your model, makes it into a product, and starts selling things you don't even know. But if you add it in your license term, if you realize that somebody is using your model for commercial purposes, you don't want them to, you can always sue them. But if you don't use these license terms, because academics, we are not supposed, we don't really know these business strategies or legal stuff. We just, made a model, upload it tomorrow. And then somebody takes your model, you'll be surprised to see how critical these models can be for design approaches. That's why I have a separate lecture on this, all right? So this is definitely useful. So in 2 minutes, I don't know whether I will be able to go over this. Maybe in the next class, the very first 5-6 minutes, I'll go over the files that I wanted to show you, just to show you the different components in the model. Meanwhile, just at home, download the file, extract it, unzip it, and see for yourself how it looks like. That way, it makes more meaning when we discuss it in class. All right? Thank you. I will see you in the next class.